Here we're going to look at pulleys and the next bit of forces and motion for our mechanics. So I'm going to go straight in with examples on this one. Number 1. And you've got these written down next to you. So particles P and Q of masses 2m and 3m are attached to the ends of a light inextensible string. The string passes over a small, smooth, fixed pulley, and the masses hang with the string taut. So let's try and get this drawn. So we've got some sort of pulley. We've got a string hanging over the top of it, like this. And then we've got two particles, P and Q, 2m and 3m respectively. So we've got P and Q. We know that P is 2m kilograms. Let's make this a bit bigger. So it looks something like this, and we've got tension in the string. So you have tension acts this way, and this way, and this way, and this way in the string. And we are told that the string is taut, so it's all nice and tight, and the pulley is smooth and fixed. That means the pulley's not going to move, and also it's smooth, means there's no kind of frictional forces happening on the pulley for the string. The system is released from rest. Write down an equation for the motion of P and the motion of Q. So we're also going to have a force acting upwards. Because remember, every force that's acting downwards, i.e. these tensions and these P and Q's weights, there'll be a force acting upwards as well. So if you think about releasing the system from rest, 2m and 3m kilograms, the 3m kilogram one is heavier. So what's going to happen is that the Q is going to go downwards and P is going to go upwards. That's what's going to happen. So P is going to start accelerating upwards when it's released, and Q is going to start accelerating downwards. So we're going to consider them separately. Part 1 is the motion of P. So if we're looking at P only, then P is this one, and P is going to go upwards because Q is heavier, and that's how the system's going to work. You can imagine this happening. Let it go, Q is going to start dropping because it's heavier, and P is going to start moving upwards. So for P, our resultant force will be upwards for P. And we've got the tension, the string going upwards this way, which is represented by the T here. And we've also got the weight due to gravity, which will be 2mg acting downwards as a force, mass times acceleration. Acceleration for the whole thing is G is 9.8 downwards, isn't it? Okay, that's our acceleration downwards. So 2mg, if the particle's going upwards, that means the T, the force in the string going this way, minus 2mg, because that's in the opposite direction, is equal to the mass times the acceleration, which is 2m times a. So that's our equation for P only. Part 2 says do Q. So for Q, the resultant force is downwards because again Q is heavier, so Q is going to be travelling in this direction. And for Q we have 3m is the mass times G acted, that's the force acting downwards. We've got T acting against the motion, and we know that it's accelerating this way. So for R going downwards, the force going down minus the force in the opposite direction is equal to mass times acceleration, 3m times whatever A is. We can't treat this all as one because things are acting on different lines, like Q is on this line here. P is on this line, Q is on this line. So it's slightly different to the connected particle stuff we've been looking at. But there's part A, 1 and part 2 done. So let's have a look at B. Find the acceleration of each mass. So we've got two equations here. We've got 1 here and 2 here. So we can solve these simultaneously in order to find our acceleration. So we can eliminate the variable. So let's look at eliminating T. So if we just line these two up next to each other, I'll just put the T first so that the T's line up here. So here's 1 and here's 2. And they've got, the t's have different signs, so if we add equations 1 and 2, we'll eliminate t. So we'll get minus 2 plus 3 here, sorry. So we'll get mg on the left. And if we add on this side, we'll get 5ma. M is on both sides, so it will cancel. So g equals 5a, and then a equals g over 5. And if we want, we can work out, because remember g is 9.8, we can work out the acceleration here. So 9.8 over 5. So you can get your calculators out if you need to. You get 1.96. Remember, this will be in meters per second squared. So there's part B. Part C, find the tension in the string. So now that we've got A, we can take one of these equations. So example, equation 1, T minus 2mg equals 2ma, and we know now that A is g over 5, or 1.96. So therefore we can sub in, so T minus 2mg is 2m times A. So T will be 2mg plus 2m times 1.96. So you might be better thinking if this is g over 5 here. And if we just tidy all this up, you can use your calculators to help you. 2 plus 2/5. Because these are both terms in mg, aren't they? So 2 plus 2/5 is 2 and 2/5, or 12 over 5. Lots of mg, or I could write this as 12 mg over 5, and this will be in newtons. So we don't know what m, we still don't know the mass yet, we don't know m, but we know we can write T as 12 mg over 5. Part D. So D says, find the force exerted on the pulley by the string. So if we just focus in on the pulley and we redraw the pulley here, then our pulley has got this T acting downwards, it's got this T acting downwards, and then there'll be an opposite force acting upwards, which is F. So the force exerted on the string is going to be, sorry, on the pulley, is going to be the two lots of T acting downwards. So that will be 2 times by the thing that we've worked out T as above. Here, that's T, so 2 lots of that, 2 times that. 2 times 12 is 24, so this would be 24 mg over 5 newtons. And then finally we can do part E. So E says, find the distance moved by Q in its first 4 seconds, assuming P does not reach the pulley. So if we're trying to find how far Q moves, that's this one, assuming P does not reach. So P is going this way, so eventually P is going to carry on and it's going to smack into the pulley, and then that might change what's going to happen here. Because the tension in the string is going to change if it hits the pulley. But we're assuming it's not, so we're assuming Q is travelling for 4 seconds. So I'm trying to find a distance, so this kind of feels like a kinematics question. So initially Q is stationary, so Q has 0 meters per second, that's acting downwards. The acceleration we know, the system starts moving with this acceleration, 1.96. So we know A is 1.96. We know T is 4. Because we're told we're asking for it in the first 4 seconds of its motion, and we're asked for its distance, that's S. So there's our 4 things that we have. We don't have V, we don't need V. So S equals UT plus a half AT squared. So S equals 0 plus a half AT squared. Calculate all this out, it's 8 times the 1.96, and we get 15.68 or 15.7 meters to 3SF. So that's how far Q moves in its first 4 seconds. And then finally, how have you used the fact that the pulley is smooth in your calculations? So if the pulley is smooth, then that means the tension in the string is the same at P as at Q. Okay, if the pulley is smooth, there's nothing resisting the motion. If you think about this, when this releases, this whole system is moving this way. So if there was some friction or it was smooth, there'd be something acting against the string this way, and that would affect calculations. And that's the first one. We're going to do the second one as a separate video, because we're running out of time in this one. So it's just one question. There's quite a lot going on, but hopefully it gives you an idea about pulleys and how we set up the tension in the string for pulleys like this. There'll always be one acting one way and one acting the other way, and you can think about where it's being pulled and how the string's working. The system is moving kind of this direction, so the string tension is going to be this way and this way, like that's this and this on this side here. That's it.